doesn't start in a mine the way most people imagine. There's no glowing silver ore sitting in a vein underground waiting to be dug out. Titanium actually begins its life hiding inside a mineral called ilmenite. And ilmenite looks like nothing special. It's a dark, sandy, almost forgettable mineral found in beach sands and rock deposits in places like Australia, South Africa, and Canada. Bulldozers and dredges scoop up massive quantities of this raw sand, and from the outside it looks like any construction site. But hidden inside every scoop is roughly 5 to 15% titanium dioxide, locked in with iron, oxygen, and a mess of other minerals that all need to be stripped away before anything resembling metal ever appears. Some of the largest ilmenite deposits on the planet sit along coastlines that most people would only ever picture as vacation spots, never realizing that the sand beneath their feet could one day become part of an airplane. The sand is first washed and separated using magnets and density separators, since ilmenite is slightly heavier than ordinary sand and reacts differently to magnetic fields. This step alone can take raw ore that's mostly waste material and concentrate it into a product that's finally rich enough in titanium to be worth processing further. But here's the part almost nobody expects. Even after this separation, what comes out still isn't titanium. It's a black, iron-rich concentrate that looks more like ground charcoal than anything resembling a lightweight aerospace metal. For every ton of raw sand collected, only a small fraction ends up as usable concentrate. The rest gets returned to the earth or repurposed for other industrial uses. That concentrate then gets shipped to a chemical processing plant where the real transformation begins, and it's a violent one. Using either the sulfate process or the chlorine process, engineers strip away the iron and oxygen bonded to the titanium, leaving behind a bright white powder called titanium dioxide, or TiO2. If that name sounds familiar, it should. This exact powder is the same compound used to make white paint, sunscreen, and even the white coating on Oreo cookies. It's strange to think that the raw material for a fighter jet's frame and the ingredient that makes sunscreen white are, at this stage, chemically identical. In fact, the vast majority of titanium dioxide produced worldwide never becomes metal at all. It stays as pigment. Only a small slice of the global supply gets pushed further down the metallurgical path toward becoming solid titanium. But turning that white powder into structural metal requires ripping the oxygen molecules away from the titanium atoms entirely, and oxygen does not let go easily. Titanium is one of the most oxygen-hungry elements on the periodic table, which means normal smelting, the kind used for iron or aluminum, simply doesn't work here. If you tried to melt titanium dioxide in an open furnace the way you'd melt iron ore, the titanium would instantly bond with oxygen in the air and turn brittle and useless. So instead, engineers use something called the Kroll process, named after the metallurgist who invented it, and this is where the transformation gets genuinely impressive. The titanium dioxide is reacted with chlorine gas and carbon at extremely high temperatures, stripping away the oxygen and converting it into titanium tetrachloride, a compound so reactive that if it's exposed to ordinary air, it will instantly start smoking. From there, that liquid is placed into a sealed reactor vessel with molten magnesium, and inside that airtight chamber, a chemical reaction pulls the chlorine away, leaving behind pure titanium metal. But this titanium doesn't look like metal at all yet. It comes out as something called titanium sponge, a porous, crumbly, gray mass that looks almost exactly like a scouring pad you'd find under a kitchen sink. It's hard to believe that this dull, spongy material is the same substance that will eventually become the skeleton of an airplane. This entire chemical journey, from raw mineral to sponge, can take several days from start to finish. And the process is so specialized that only a small number of facilities in the entire world are capable of producing titanium sponge at industrial scale. That sponge then gets crushed, sorted, and blended with small amounts of other metals, usually aluminum and vanadium, to create specific titanium alloys with different strength, weight, and heat resistance properties depending on their final use. The blended sponge is compacted and welded into large electrodes, which are then melted down using a process called vacuum arc remelting. Inside a sealed vacuum chamber, An electric arc melts the electrode from the bottom up, drop by drop, into a water-cooled copper mold. And this step has to happen inside a vacuum for one very specific reason. Even trace amounts of oxygen or nitrogen from ordinary air can weaken the final metal at a microscopic level, creating tiny defects that could someday turn into cracks thousands of feet in the air. One tiny contamination event during this melt can compromise the structural integrity of an entire aircraft component years later. To be extra safe, the biggest aerospace suppliers melt the titanium not once, but 2 or even 3 times in a row, each time in a fresh vacuum chamber, slowly refining out any last trace of impurity. Engineers run ultrasonic scans and X-ray inspections on the resulting ingots afterward, searching for any hidden void or inclusion too small for the human eye to catch. What comes out of this process is a massive cylindrical ingot of pure titanium alloy, silver gray and incredibly dense looking, weighing anywhere from a few hundred to several thousand pounds depending on what it's destined to become. From there, the ingot is reheated and forged, hammered and pressed under enormous hydraulic force, while still glowing hot, gradually shaping it into billets, bars, plates, or sheets. This is where titanium's strange dual personality really shows itself. It has to be heated to precise temperature windows, because if it's forged even slightly too cold, the metal can crack internally in ways that won't show up until much later. If it's forged too hot, the grain structure inside the metal weakens. Engineers monitor these temperatures constantly because titanium simply doesn't forgive mistakes the way softer metals do. A single misjudged degree can mean the difference between a component that lasts 30 years and one that fails without warning. Once shaped, the titanium moves to machining, where computer-controlled cutting tools carve the rough shapes into their final precise forms. Turbine blades, structural spares, surgical implants, bicycle frames, or the housing for a deep-sea submersible. And here's a fact that surprises almost everyone. Titanium is notoriously difficult to machine because it doesn't conduct heat away from the cutting tool the way aluminum or steel does. The heat generated by cutting stays concentrated right at the tip of the blade, which means titanium can actually melt and weld itself onto the cutting tool mid-process if the machinist isn't using the right speed, coolant, and cutting angle. A single miscalculated cut can ruin a piece that took weeks to reach this stage, which is why titanium machining is considered one of the more specialized and expensive skills in modern manufacturing. For medical implants specifically, the surface finish matters just as much as the shape. Titanium has a remarkable natural property called osseointegration, meaning living bone cells will actually grow directly onto and fuse with a titanium surface over time, essentially treating the implant as part of the body rather than a foreign object. That's the reason a titanium hip or dental implant can last for decades without the immune system rejecting it. The surface is sometimes deliberately roughened at a microscopic level, specifically to encourage bone to lock onto it more securely. Some implants are even textured using lasers or acid etching, creating a surface pattern invisible to the naked eye, but perfectly suited for bone cells to grip onto. For aerospace parts, the final step is usually anodizing or coating the surface, which builds up an ultra-thin oxide layer that gives titanium its famous, almost permanent resistance to corrosion. This oxide layer is only a few nanometers thick, but it's remarkably self-healing. If it gets scratched, exposure to oxygen in the air instantly regenerates it. That's the real secret behind why titanium survives decades in seawater, jet fuel, and even inside the human bloodstream without breaking down the way steel or aluminum eventually would. By the time a finished titanium component reaches an assembly line, whether it's bound for a commercial airliner, a naval submarine, or an operating room, it has been mined from beach sand, chemically stripped of oxygen, melted in a vacuum 3 separate times, forged under thousands of pounds of pressure, and machined to tolerances measured in thousandths of an inch. What started as a dull, forgettable black mineral has become one of the most trusted materials in engineering, strong enough to hold together a jet engine and safe enough to spend the rest of someone's life inside their own body. Precision, chemistry, and patience hidden behind a metal most people never think twice about, until now.